So we're in your chemistry book. We're in chapter 11, section 3, and we're going into talking about the alkaline earth metals. Now in section 2, we talked about the alkaline metals. And so here's your periodic table. So where are these metals located? We already said a lot of the non-metals are over on this side, right? And the metals being most of the other whole part of the periodic table. So, but the alkaline metals, which we went over last time, are in column 1. Lithium, sodium, potassium, rubidium, and cesium. So now we're going to go into column 2. And so these are the alkaline earth metals. You put the word earth in there. So we have beryllium, magnesium, calcium, strontium, barium, and radium. So this whole column. So let's begin, and we're going to be talking about the alkaline earth metals. They're never found naturally, just like alkaline metals. They're never found naturally as free elements. They're always found as ions because they're very reactive. But they're always found as 2+ ions. Remember, the alkaline metals were 1+ ion, and the alkaline earth metals would be 2+ ions. Many are insoluble in water. In the crust of the earth, you'll find phosphates, sulfates, carbonate ores. You'll find alkaline metals. Also, beryllium and magnesium are silicate ores. You find them in the midst of silicon. The oceans have an inexhaustible supply of magnesium. How much magnesium are in the oceans? 6 million tons of magnesium per cubic mile of seawater. That's a lot of magnesium in the ocean. Magnesium actually composes of 1.9% of the Earth's crust, and that's the 8th most common element in the crust of the Earth. So magnesium is very common. Calcium ranks as the 5th. So, and the 5th in the crust, most common in the crust, and the 3rd most common metal altogether, actually, in the midst. So calcium is very, and you probably know, you've heard a lot about calcium too. So calcium ranks as the 5th most abundant element and the 3rd most abundant metal. So about 3.4% of the mass Earth's is in calcium. So calcium is one of the common alkaline earth metals. So let's talk about the harder and denser than the alkaline metals. The alkaline earth metals are still soft and less dense, but a little bit harder than the alkali metals. And they also react less vigorously than the alkali metals, even though, because they have 2+2. All but beryllium are silvery colored, and beryllium is white, but all the rest are silver colored. Though higher than those for group 1 in the alkali metals elements, the ionization energies of group 2 are still low, making them very reactive. So very reactive. So they're reactive, almost as reactive as the alkali metals. So alkali metals, and now we're talking about alkali earth metals. They easily lose electrons. And these alkaline earth metals usually form ions, ionic compounds. So now let's talk about water. Have you ever had hard water? Especially if you have a well, you probably have experienced hard water. What makes the water hard? Well, we find some of these alkali earth metals, such as calcium and magnesium, make the water hard. Also, iron does. So iron's another type of metal, but calcium and magnesium are two that definitely do. And hard water means that the water doesn't lather very well. You know, in fact, when you put soap with it, sometimes it kind of scums up. And so in finding this calcium sulfate is one of the, calcium sulfate is limestone deposits of calcium in the midst of sulfates, and this causes hard water. So in your book, it talks about two different kinds of hard water too. So here's equations here, and limestone, which is calcium carbonate. Limestone here, you should know that whenever you see calcium carbonate, it's limestone. Limestone is definitely calcium. And it combines with carbon dioxide and water, forming calcium bicarbonate. So boiling water that contains calcium bicarbonate decomposes, and this we get water and carbon dioxide and calcium carbonate. And these deposits of calcium carbonate are known as boiler scale. What are boiler scale? Boiler scale are these deposits that are made, like if you have a teapot and you have like scum on the teapot, kind of a calcium buildup. So these are these deposits on boilers and hot water and stuff. So they're basically scumming up, or should I say depositing calcium. So in boiler scale, the scaling it. So when you say to descale something, is to get rid of the calcium carbonate. So water containing calcium or magnesium bicarbonate is called a temporary hard water, since the hardness can be removed. The water can be softened by boiling it and precipitating the hard water out, and out comes the calcium and magnesium carbonate deposits, right? So you can get calcium and magnesium out of the hard water pretty easily. But there's the type of permanent hard water. Permanent hard water is a little different because it has sulfates in it, so sulfur. So we're talking not with calcium and magnesium, but we're going to be talking about sulfate, sorry. So water containing sulfates of calcium or magnesium cannot be softened by being boiled. This is termed permanent water. So it's not just calcium carbonate, it's calcium sulfate. So when you have the sulfur mixed in there. Both temporary and permanent hard water can be softened for use in washing clothes by adding washing soda. So if you bring in washing soda in your washing detergent here, and sodium carbonate, and you combine it with water, then you can actually soften even the hardest water. So, and here's an equation that has to do with that process. Water may be best softened by using synthetic organic materials called ion exchanges. So let's talk about these ion exchanges. Here's a picture of an ion exchange setup. Cartridges containing the ion resins are up here on down as the water goes through. So basically, when you say cation exchange, you're going to be exchanging positive ions. If it's anion exchange, that's going to be changing negative ions, right? So cation exchange resins consist of large molecules known as polymers that form a network that contain chemically bonded negative charged groups. And let's go on to the next page. Sulfonate. So, and this negative charge is usually balanced by sodium hydrate ions. When you say cation, you're going to be exchanging positive cations. Anion exchange resins contain positively charged groups that are going to be able to change the negative. So let's go on and see a picture of it. As water passes through a cation exchange, the hard water ions such as calcium, are replaced by sodium. So that's the exchange. See how the calcium is a cation, it means a positive ion, and it's changed by sodium. So that's why they call it cation exchange. And there is a equation there, as you see. Basically, you are exchanging in the midst the cations, calcium coming in, exchanging onto here. You see, this is where ions resin follows, where Z, whatever it is, represents the cation exchange resin. So they put together that equation. Since the hard water ions are removed, the water is softened. If the water is then passed through an anion exchange resin, the negative ions in the water are replaced by OH, basically hydroxide ions. So they're negative ions, just the negative ions being exchanged. See here, as the positive ions were exchanged, exchanging calcium for the hydrogen positives. Here we have the negative ions being exchanged. So the resulting water is called deionized since the OH and the hydrogen ions combine to form H2O water. So making the water soft. So it sounds very complex, but just think, cation exchange is exchanging a certain cation of calcium with a hydrogen ion of water. And same thing with the negative is changing for the hydroxide ion. OH is that, a negative one in the midst of the exchange. So, okay, we'll go over that a little bit and a little bit too more. So, and then we have limestone caves. So limestone caves, when you think of limestone, you're going to have to think of calcium. So calcium, the equation here, it says reaction 10-6 and 11-6. Let's go back to that reaction, 11-6. See if we can get it. Here's a picture of it, limestone reaction here. So we have the limestone reaction there with limestone added with carbon dioxide and water, and you get calcium bicarbonate. So, and also onto this reaction too, where boiling the water with calcium bicarbonate decomposes the bicarbonate to reciprocate and bring back the limestone. So those two things are in limestone caves, in fact. So these underground limestone caves may be dissolved by water containing carbon dioxide and other acids in the caves, and these form these icicle-like stalactites and stalagmites. So I'm sure you heard of those. And these are all made of limestone. Under certain conditions, calcium carbonate may be rapidly deposited in a cave as water drips from the cave ceiling, and they turn into stalactites and stalagmites. So when you think of limestone, think of calcium. Basically think of the calcium reacting with calcium carbonate reacting with water and carbon dioxide. Okay, uses. So what do we have uses? All alkaline earth metals but beryllium are prepared by electrolysis of molten chloride at high temperatures. So they take chloride and put it at high temperatures so that they can actually divide out the calcium and chloride here and bring in what they want to get out is the pure calcium. So they could put it through electrolysis. So just to let you know on that subject. The uses of beryllium. Beryllium they use basically for windows in X-ray tubes because it has a low density and high strength. They also use it in the structure of aircraft. If you take beryllium and put it with a copper alloy, you'll get a very strong and hard elastic type metal. And they use these in springs and in non-sparking tools because they don't make sparks. Beryllium nickel alloys are resistant to seawater, so they use beryllium nickel on ship parts so that they don't get corroded, right? So pure beryllium is very toxic. So if you had some beryllium, you surely would not want to be ingesting it or, coming close to it. But as for the combination with the alloys of copper and nickel mixed with it, you get these other important metals. So now let's talk about magnesium. Magnesium, what do you use? What's magnesium? Well, magnesium burns in the air as brilliant, beautiful flame. So they use it a lot for fire-producing bombs and fireworks in many areas. Also, the old flash bulbs used to be magnesium. It's very light, magnesium. The metal is very light, but very strong. The alloy of magnesium mixed with aluminum is even stronger. And they use the alloy with magnesium. Here's a picture of it here. What is this? It's a sports car wheel because it's so strong. It's mixed with magnesium and aluminum. And ladders, patio furniture, airplanes, spacecraft, you name it, made of this strong metal. Magnesium. I didn't know magnesium could be a strong metal, but that's what it is. So let's see here. Alkali earth metal compounds. So let's talk about, did we talk about calcium? Yeah, here's calcium, okay. Alkali earth metal compounds, more important than free alkaline earth metals are their compounds, especially those of calcium, because calcium combines with a lot and makes a lot of different types of substances and as being that metal. So calcium compounds are very important, and they have that ion of 2+ ion. Calcium in our body. Our bones and teeth need calcium, are made of calcium actually. Our nerves, our eyesight needs calcium. Muscles, our muscle contractions has to do with calcium in our body. And then calcium carbonate is limestone, as we said before, and that's very important. Actually, and other minerals such as aragonite and calcite are in marble. So you go from limestone to marble. So marble is made of calcium. Also shells in the sea, as you pick up shells in the sea, they're made of calcium. So if you wanted to get marble, you would take limestone and put through the process of that into making marble. And marble was used, both limestone and marble were used in ancient of days. So let's see. Also, calcium is in volcanic ash too. So this is pretty important right here that we know. Calcium oxide is known as lime, right? So when you have calcium and oxygen as lime or quicklime, and it's most heavily used chemical in the United States. One that we use a lot. And it's reacted with water, it becomes slaked lime. So here's slaked lime, calcium OH2, so CaOH2. So just think of calcium oxide known as lime, and it's very, very important because it's most heavily used in the United States. Calcium carbonate, limestone, which we've talked about already, is used extensively in iron ore reduction. It's getting the iron out of the ore so that we can use iron and steel. And it's also used in cement manufacture. Portland cement is a limestone that is heated with clay. Clay has aluminum silicate in it. But it's heated in this oven or this kiln to produce clinker. And these clinker are these pebble-sized lumps of calcium and silicates and aluminates in the midst. And these are ground into a powder and mixed with a few percent of gypsum in the midst of all we're doing. Remember, we're putting together this Portland cement. You mix this with gypsum, very important, mixed with gypsum, and this is how you make cement. And gypsum controls the rate at which the cement hardens. So the cement is added to water, sand, and aggregate, and it crushed there and added to, so it doesn't shrink to form what's called concrete. So cement forming concrete. Just remember, this is calcium carbonate limestone going on, adding gypsum, all these things happening to it to be able to produce, first of all, cement with added gypsum, and then onto concrete as it's added with water to it too. It says, contrary to popular belief, cement and concrete do not harden by drying out. Rather, the setting and hardening process involves chemical reactions of the cement compounds with water, known as hydration reactions. And that's how it hardens. I didn't know that either. So, and also let's go on to magnesium here. So we kind of went over magnesium, but there's a suspension of magnesium hydroxide that's known as milk of magnesia. Have you ever heard of it? And it's used as an antacid for stomach and also as a laxative. And also there's another magnesium, and here's the magnesium sulfate. And magnesium sulfate here, here's the formula, is known as Epsom salts. Have you ever heard of Epsom salts? So when you're putting Epsom salts in a hot bath to reduce your swelling from bruises or sprains or just relaxing at that time, you're relaxing in magnesium. And so that magnesium is basically, reacting to your body to help you in this area. So anyway, it's also used as a laxative and a cathartic. Magnesia oxygen. Magnesia, which is called magnesium and oxygen together, is an excellent insulator and is resistant to the decomposition at high temperatures. So they use this in bricks that are to have high temperatures and furnaces and such, so they can process iron ore at very high temperatures. So magnesium is used at very high temperatures in these bricks. Now, strontium. Strontium is basically used for signal flares. Here's a picture. Signal flares and fireworks, since they produce a brilliant red scarlet flame when burned. So they use strontium metal as a flame. Barium, most barium compounds are toxic. Barium sulfate, though, is not poisoning because it's a very low solubility and it's used in taking x-rays. So they give you barium so that they could take an x-ray of your gastrointestinal tract. So in x-rays. So let's kind of go over this table of major sources and commercial uses of alkaline earth metals. Beryllium, aluminum silicates, including beryl, and here we got that, the sources. Very strong, lightweight, corrosive, resistant for x-ray tube windows, and beryllium. Magnesium here, carbonates and silicates and seawater. Remember, in seawater there's lots of magnesium. Alloys for airplanes. They build airplanes, high-performance cars, ladders, patio furniture, flash bulbs, pyrotechnics, which is fireworks, bombs, refractory bricks. Remember the real bricks that can hold at high temperatures. Milk of magnesia, Epsom salts. A variety of things with the magnesium. Onto calcium. Limestone and gypsum and fluorite and apatite. These are, you can see lime. Here is the formula for lime, which is, I think, a question. Calcium oxygen is lime. Slaked lime is calcium hydroxide here. It's widely used as bases in chemical industry. Cements, limestone. Of course, this limestone is calcium carbonate. We went over that multiple times. Used in iron ore reduction to get the iron out of the ore, and cement production and pollution control. Onto strontium, and the salts are used for pyrotechnics like that red flame, fireworks that are of red, Barium is used in medicine and gastrointestinal x-rays. also in white paints. And barium nitrate is used for pyrotechnics to give a green flame. So just remember, okay, we have 5 earth metals, very important. So let's go on to go over some of the questions here and we'll be done with this chapter. Differentiate, let's see. Differentiate between the causes of temporary hard water and permanent hard water. As you remember, they're calcium and magnesium deposits, but they're mixed into whether they're calcium carbonate or whether they're calcium sulfate. So just regular hard water, it has calcium and magnesium, and it can be removed usually by boiling it and precipitating it out. But the permanent hard water contains sulfates, and to get a sulfate out, you can't do it in a very easy way. You know, the sulfates, so they're considered permanent. So if you have magnesium sulfate or calcium sulfate with the sulfur in it, it's going to be called hard water. Show an equation, show by equation one cause of boiler scale. Well, I'm not going to go over there. We went over that already. So basically, it's in your book. So the cation exchange, okay, let's go on to next. Explain how cation exchange resin softens water. You're exchanging those cations, you know, from calcium to something else. So in the midst, the calcium is being exchanged into another polymer, and in doing that, you know, that exchange, you'll end up coming out with a soft water. So give one use of each alkaline metal. We went through those all right on this chart up here, so we're not going to do that. Give the chemical formula of each of the following, and we went over that too, with Epsom salts, and all these are up here. So magnesium, limestone, we went up. Let's point them out here. Let's just go up here. We see 4, let's see, here's limestone right here, calcium, CaCO3, limestone, onto, let's see, lime right here is calcium oxygen right here. Slaked lime is calcium hydroxide right here. Limestone being up here. Milk of magnesia, let's see if we have that on here. Maybe we don't have it on there, let's see. Oh, here's milk of magnesia, magnesium hydroxide right here. Epsom salts, magnesium sulfate here. And onto magnesia, which is this hard brick. So all of them written up there. I just have to bring them down, right? Give one compound of each alkaline metal, each alkaline earth metal and its use. So the same thing. You can look up here. Each one of these are compounds, and just put them down here if you want. So I'm not going to go over those. So that's about it. A little review here. We're talking about calcium, Ca, magnesium, beryllium, strontium, barium. Limestone caves are calcium carbonate, right? This is the formula. And this is calcium bicarb, and they're making the stalactites and stalagmites. How we make cement. We have cement of the lime, calcium oxide onto the slaked lime, which is hydroxide, and onto limestone, going on to making cement, adding gypsum to it, and you'll get cement, and then adding water for concrete. Milk of magnesia, we went over these here, I'm not going to go over those. And so, and of course, the boiler scale is, those are those deposits that are of calcium, magnesium, making hard water. Cation exchange with sulfonate, basically. Anion exchange with hydroxide exchange here. Permanent high water has sulfates, right? So anyway, just a review there. So that's it.